Welcome. Here at the Urban Herald, we tackle complex topics, try to cut through the noise, and really get to the heart of things. Today, we're exploring something truly monumental, a single scientific achievement that, well, changed the world forever, the atomic bomb.
Our mission is to unpack how these weapons work, their history, their legacy, give you the key insights you need.
Absolutely. And it's fascinating, isn't it, how the science, the history, the ethical questions,
Mhm.
they're just completely inseparable with this invention. Understanding it isn't just history class stuff. It's fundamental to being an informed citizen today in the nuclear age we still live in.
Definitely. So let's start right at the beginning. For anyone maybe less familiar, how would you explain an atomic bomb? What's the core idea and what makes it so different from, say, dynamite?
Right. Well, at its most basic, an atomic bomb harnesses energy from nuclear reactions, specifically nuclear fission splitting atoms.
Mm.
Conventional bombs, like dynamite, they rely on chemical reactions, burning, basically. The energy locked inside an atom's nucleus is just vastly, vastly greater. We're talking orders of magnitude more powerful. And that power difference is staggering. I mean, the bomb used on Hiroshima, little boy, it had about 50 kilograms of uranium-235, right?
That's right, about 110 pounds.
And yet that small amount had the explosive force of 15,000 tons of TNT.
15 kilotons, yeah. The energy density is almost unbelievable compared to chemical explosives. It instantly changed the scale of warfare.
It really did.
And if we connect this to the underlying science, it all comes back to Einstein's famous equation, EMC-odd.
Ah, yes. The classic.
It tells us that mass and energy are interchangeable, that a tiny amount of mass, if converted, releases an enormous amount of energy. That's the bedrock principle, not just for weapons, but for nuclear power, too. It's the key that unlocked the atom's potential.
And unlocking it for weapons happened during World War II with the Manhattan Project. Absolutely massive undertaking, led by the U.S., but with key help from the U.K. and Canada.
Right. The scale was just unprecedented, almost 130,000 people working on it.
And the cost. About $2 billion back then, which is what, $27 billion today?
Something like that, yeah. A colossal mobilization of scientific and industrial power. You had J. Robert Oppenheimer leading the scientific design at Los Alamos,
The father of the atomic bomb.
as he's often called. And then Major General Leslie Groves overseeing the whole massive program, logistics, security, everything.
And you mentioned international collaboration. There's an interesting story about a British physicist, Mark Oliphant.
Yes, that's a fascinating detail. In 1941, Oliphant visited the U.S. and was, well, frankly shocked to find that crucial British research on uranium-235's potential stuff his team had done wasn't really being acted upon. The reports were just sort of sitting there.
Really?
Yeah, so he directly pushed American scientists like Ernest Lawrence and Oppenheimer, basically saying, look, this is feasible, you need to take it seriously. His intervention really helped galvanize the American effort. Shows how crucial that exchange was.
Wow. And all that effort, the science, the engineering,
Mm.
it led to the first test, Trinity.
July 16th, 1945, New Mexico desert. That was the test of the implosion-type design, the more complex one.
And it worked.
It worked spectacularly, terrifyingly. And very soon after, the two types of bombs developed by the project were used.
Little boy, the uranium gun type over Hiroshima, and Fat Man, the plutonium implosion type over Nagasaki.
The world changed in those moments.
Okay, let's get a bit deeper into that science. Nuclear fission. You said it's about splitting atoms. How does that actually release so much energy?
Right. So you take a heavy atomic nucleus, like uranium-235 or plutonium-239. These are isotopes that are inherently a bit unstable. If one of these heavy nuclei absorbs a neutron, it becomes very unstable.
Yes.
So unstable, it splits apart, usually into two smaller nuclei.
Okay.
But here's the key. When it splits, the total mass of the two smaller pieces is slightly less than the mass of the original heavy nucleus plus the neutron.
A tiny bit of mass just disappears.
Effectively, yes. It's converted directly into energy following Imasi-Font. And because c squared, the speed of light squared, is such a huge number, even a tiny amount of mass becomes a tremendous amount of energy.
How much energy are we talking per split?
Around 200 million electron volts per fission event. That might not sound like much, but remember, that's from a single atom. Compared to a chemical reaction like burning, it's millions of times more energy per atom involved.
Right, that's the core of its power.
Exactly. That's why nuclear reactions are so potent.
So one atom splits, releases energy, but for a bomb, you need more than that, right?
Yeah.
You need it to keep going.
Precisely. That brings us to the chain reaction. This is crucial. When that heavy nucleus fissions, it doesn't just release energy and those two smaller nuclei. It also releases, on average, 2 or 3 new neutrons.
Ah, I see where this is going.
Yeah, those newly released neutrons can then go on to strike other nearby heavy nuclei.
Causing them to fission.
Right. And they release more neutrons, which hit more nuclei, which release more neutrons. It becomes a cascade, an exponentially growing reaction.
A chain reaction.
Exactly. This raises an important question, though. How do you control this? Or, in the case of a weapon, how do you ensure it happens incredibly fast and all at once to unleash that energy rather than just fizzle?
And that comes down to the materials, doesn't it? You mentioned uranium-235 and plutonium-239. What's special about them?
These are the main fissile materials. That means they can sustain these nuclear chain reactions. Uranium-235 is interesting because it's found in nature, but it's really rare. Only about 0.7% of natural uranium is U-235. The rest is mostly U-248, which doesn't fission easily with the kind of neutrons released.
So you need to separate it out.
Exactly. That's uranium enrichment, a very difficult, very energy-intensive process to increase the concentration of U-235.
And plutonium.
Plutonium-239 isn't found naturally in any significant quantity. It's actually man-made. You create it inside nuclear reactors when uranium-238 absorbs a neutron and undergoes some transformations.
Okay. And plutonium has an advantage for weapons.
It does, in some ways. Its critical mass tends to be smaller than U-235's, meaning you need less of it to start that chain reaction. That makes for potentially smaller, lighter weapons.
Let's talk about critical mass. We hear that term a lot. What exactly does it signify?
Critical mass is basically the minimum amount of fissile material you need under specific conditions for a chain reaction to become self-sustaining.
So if you have less than that amount.
It's subcritical. When atoms fission, too many of the released neutrons escape out of the material before they hit another nucleus. The reaction just dies down.
And if you have more?
Then it's supercritical. Enough neutrons find other nuclei to hit, the reaction grows exponentially, and, well, you get an explosion. The goal in a weapon is to bring subcritical masses together very quickly, or to compress a subcritical mass to make it supercritical almost instantly.
And critical mass isn't just about the amount, is it? Other things affect it.
Oh, absolutely. It's not a single fixed number. It depends heavily on the material's density. Squeezing it makes it more likely neutrons will hit something, because shape matters too. A sphere is the most efficient shape, minimizing surface area for neutrons to escape. Purity of the material is important, and crucially, what's around the material.
Like a reflector.
Exactly. You can surround the fissile core with a dense material called a tamper, or neutron reflector. Its job is twofold. It helps hold the core together for a few extra microseconds as it starts to explode, allowing more fissions to happen. And it literally bounces escaping neutrons back into the core.
They get more efficient.
Much more efficient. It significantly reduces the amount of precious fissile material needed to reach critical mass. And just to reiterate that point about energy from mass, the mass defect, it really is mind-boggling. In Hiroshima, they had 64 kilograms of uranium. But only about 1 kilogram actually underwent fission.
Just 1 kilo.
Roughly, yeah, less than 2% of the material. And yet that tiny conversion of mass into energy produced a 15 kiloton blast. It just shows the sheer scale of energy locked inside the atom.
Incredible inefficiency, yet incredible power.
Precisely.
So knowing the science, how did they actually build these things back in 45? What were the main designs?
There were 2 primary designs that came out of the Manhattan Project. The first was the gun-type assembly.
Like a little boy.
Exactly like Little Boy used on Hiroshima. It was the simpler concept. You basically have 2 subcritical pieces of uranium-235. One piece, the bullet, is fired using conventional explosives down a sort of gun barrel into the other piece, the target.
And when they slam together?
The combined mass instantly becomes supercritical and the chain reaction starts. Simple, relatively reliable.
So reliable they didn't even test it before dropping it.
That's the remarkable thing, yeah. They were confident enough in the physics and engineering of that relatively straightforward mechanism. But as we said, it was inefficient. A lot of that expensive U-235 didn't get used in the reaction.
Okay, so that's the gun type. What was the other one?
The other was the implosion-type assembly. This was used for the Fat Man bomb, dropped on Nagasaki, and it used plutonium-239.
Why the different design for plutonium?
Plutonium, specifically the isotope Pu-239 produced in reactors, has a higher rate of spontaneous fission. Atoms just splitting on their own, releasing neutrons. In a gun-type bomb, which takes milliseconds to assemble, these stray neutrons could start the chain reaction too early, before full supercriticality is reached. You'd get a fizzle, a much smaller explosion.
Ah, so you need a much faster method.
Much faster. That's where implosion comes in. You start with a subcritical sphere of plutonium. Around it, you place carefully shaped charges of high explosives, like segments covering the sphere.
Okay.
When these explosives are detonated perfectly simultaneously, and this is the tricky part, they create a powerful uniform shockwave moving inward.
Compressing the plutonium.
Exactly. Squeezing that plutonium sphere very rapidly, increasing its density dramatically. This compression pushes the plutonium into a supercritical state in microseconds.
Microseconds. That timing must have been incredibly difficult.
Absolutely. What's fascinating here is the engineering challenge. Those explosive lenses had to detonate within maybe a millionth of a second of each other. Any significant asymmetry in the implosion, and the plutonium core wouldn't compress evenly, and the bomb wouldn't work properly. It was a huge technical hurdle.
And these fission bombs were just the start, weren't they? Then came thermonuclear weapons.
Right. Hydrogen bombs, or H-bombs. These are a step beyond. They actually use a primary fission explosion, like a small atomic bomb, to create the intense heat and pressure needed to trigger a secondary reaction. Nuclear fusion.
Fusion, joining atoms together rather than splitting them.
Correct. Fusing light nuclei, like isotopes of hydrogen, deuterium, and tritium. This releases even more energy per unit mass than fission.
Leading to much bigger bombs.
Much, much bigger. The Soviet Union's Tsar Bomba test in 1961, that was a multi-stage thermonuclear device. Its yield was around 50 megatons, that's 50 million tons of TNT equivalent, over 3,000 times more powerful than the Hiroshima bomb. It showed the terrifying potential of fusion.
So if we break down an atomic bomb, either fission or the fission part of a fusion bomb, what are the absolute essential components?
Okay, key pieces. First, obviously the fissile core. That sphere or assembly of uranium-235 or plutonium-239. We mentioned the Fat Man core was about 6.2 kilograms of plutonium, roughly softball size before compression.
Right.
Then you need the high explosives. In the gun type, it's just to fire the bullet. But in implosion, it's thousands of pounds, like the 5,300 pounds in Fat Man, shaped precisely to create that converging shockwave.
Got it. What else?
You need a neutron initiator, a small device, often using materials like polonium and beryllium, placed at the center of the core. Its job is to release a burst of neutrons at the precise moment of maximum compression to reliably kickstart the chain reaction. Timing is everything.
Okay, initiator.
Then you usually have the neutron reflector or tamper we mentioned, dense material around the core like uranium-238 or tungsten to bounce neutrons back in and help hold the core together momentarily, boosting efficiency.
And
Finally, the casing and delivery systems. The bomb needs a sturdy structure to hold everything together, survive delivery, maybe by aircraft. It needs aerodynamic shaping, and often things like barometric sensors to trigger detonation at a specific altitude above the ground, which maximizes the blast effects over a wider area. It's a complex package.
a terrifyingly complex package. Let's walk through that detonation sequence, that tiny fraction of a second. How does it start?
Okay, so it begins with the trigger signal. In the gun-type little boy, that signal fires the conventional charge, propelling the uranium bullet down the barrel. It takes maybe a few milliseconds to travel and hit the target mass. As they merge, supercriticality is achieved. The chain reaction begins.
Slower, relatively speaking.
Right. Now compare that to the implosion Fat Man. The trigger signal goes to detonators on all 32 explosive lenses simultaneously.
The crucial simultaneous part.
Absolutely. Those explosives detonate, sending that symmetrical shockwave inwards. It hits the plutonium core, compressing it from maybe softball size down to, say, tennis ball size in just microseconds. Density shoots up.
And at peak compression.
At that exact moment, the initiator at the center releases its burst of neutrons. And because the plutonium is now dense and supercritical, those neutrons find plenty of nuclei to hit, and the chain reaction takes off like wildfire.
And how fast does that chain reaction grow?
Astonishingly fast. Each generation where neutrons from one set of fissions cause the next set takes about 10 nanoseconds. That's 10 billionths of a second.
Wow.
In a typical bomb, maybe around 80 generations occur before the bomb's own energy blows it apart, stopping the reaction. But here's the truly mind-bending part. Something like 99.9% of the total energy is released in the last 7 generations.
The last 7.
Yeah, which take only about 0.07 microseconds, 7/100th of a millionth of a second. It's an almost instantaneous, incomprehensible burst of energy release. That's the core of the explosion.
And that energy burst creates the fireball.
Exactly. The incredible energy heats the weapon components and the air immediately around it to tens of millions of degrees Celsius, hotter than the sun's core. Initially, a lot of this energy is in the form of X-rays. These X-rays are absorbed by the surrounding air very quickly, heating it intensely. This superheated air becomes a glowing plasma ball, the fireball.
How big does it get?
It expands rapidly. For a 1 megaton bomb, the fireball could be a mile across within about 10 seconds, and it's incredibly bright, many times brighter than the sun, capable of causing blindness miles away. That thermal radiation is a huge part of the destructive effect.
And the mushroom cloud, that iconic image.
That forms as the fireball, being incredibly hot and buoyant, rises rapidly through the atmosphere like a gargantuan hot air balloon. This creates a powerful updraft. It sucks cooler air in from the sides and pulls dust, debris, and the vaporized weapon materials upwards, forming the stem of the mushroom. As it reaches higher altitudes where the air is thinner, the hot gas cloud spreads out horizontally, forming the cap. While it looks dramatic, its grim significance is that it carries radioactive material to fall out high into the atmosphere, where winds can then disperse it over large areas.
Right. Let's talk more about those effects. Beyond the initial flash and fireball, what are the main ways an atomic bomb causes destruction?
We usually break it down into a few key categories. First, and often carrying about half the bomb's energy, is the blast wave.
The shock waves.
Right. That rapidly expanding fireball creates an incredibly sharp pressure front moving outwards faster than sound initially. We measure its strength in overpressure pounds per square inch, psi, above normal air pressure.
And what can that pressure do?
Even 5 psi is enough to collapse most houses. Get up to 10 psi and you're destroying reinforced concrete buildings. The blast wind following the shockwave adds to the destruction, and studies show things like streets and buildings can channel or reflect the blast, causing complex damage patterns in cities.
Okay, blast wave is number one. What's next?
Next is thermal radiation, the heat flash. This carries maybe 35–45% of the energy. It's intense electromagnetic radiation, light, and heat traveling outwards at the speed of light.
So it arrives almost instantly.
Instantly, it can ignite fires, wood, fabrics, anything flammable miles away from ground zero, and cause severe burns on exposed skin.
The flash burns.
Yes, it's sobering. 2/3 of the injured survivors in Hiroshima had flash burns. It can even create eerie thermal shadows where objects blocked the heat, leaving an unburned outline on a scorched surface.
Horrifying. Okay, blast, heat. What else?
Then comes nuclear radiation and fallout. This is maybe the most unique and insidious effect of nuclear weapons. There's initial radiation released right at the moment of detonation, mainly gamma rays and neutrons. Intense doses close to the blast cause acute radiation sickness, often fatal within days or weeks.
And then fallout.
That's the longer-term hazard. The bomb's radioactive debris plus irradiated soil and dust sucked up into the mushroom cloud falls back to Earth over hours, days, even weeks. This fallout contaminates ground, water, food sources, emitting radiation.
And the long-term health effects.
Studies of the Hibakusha, the survivors of Hiroshima and Nagasaki, tragically documented increased rates of cancers, especially leukemia, appearing years later. Also things like cataracts and distinctive scar tissue called keloids. It's estimated radiation caused about 6,000 additional deaths in Hiroshima in the first month alone among those who survived the initial blast and heat.
Just awful. Is there anything else?
One more significant effect, especially relevant today, electromagnetic pulse, or EMP.
Ah, EMP. We hear about that. How does a bomb cause it?
The intense burst of gamma rays from the explosion interacts with air molecules in the atmosphere, stripping electrons away. These moving electrons create rapidly changing electric and magnetic fields that propagate outwards like a radio wave, but an incredibly powerful one.
And that damages electronics.
Exactly. It can induce damaging currents and voltages in electrical conductors, power lines, communication cables, antennas, and the circuitry inside electronic devices. A high-altitude nuclear explosion, detonated miles up, could potentially generate an EMP capable of disrupting or destroying unprotected electronics across an entire continent.
Was this known from the start?
The effect was noticed even during the Trinity test in '45. Shielded recording equipment malfunctioned due to the electromagnetic interference. In our modern world, so utterly dependent on electronics for power grids, communications, finance, everything, the potential impact of EMP is a major concern.
It really puts the scale of destruction into perspective. Blast, heat, radiation, EMP. And this all became horrifyingly real in August 1945, Hiroshima, August 6th, Nagasaki, August 9th. The first and so far only times these weapons have been used in war.
That's right, little boy on Hiroshima, estimates vary, but perhaps 70,000, 80,000 people killed instantly. By the end of 1945, maybe 140,000 dead, something like 80% of the city center just flattened.
In Nagasaki.
Fat Man exploded over Nagasaki. A different geography, more hills, perhaps limited the blast slightly compared to Hiroshima, but still utterly devastating. Maybe 40,000 killed instantly, perhaps 70,000, 80,000 by year's end.
And as you said, the deaths didn't stop there. Radiation effects continued for decades. The total toll across both cities eventually approached maybe 450,000 people.
Staggering numbers. And those events didn't just end World War II. They irrevocably ushered in the nuclear age and, very quickly, the Cold War arms race.
Because the U.S. monopoly didn't last long.
Not at all. The Soviet Union helped significantly by espionage that obtained secrets from the Manhattan Project, tested their own atomic bomb in August 1949. That shattered the American monopoly and really kicked off decades of intense competition. This raises an important question looking back. How did that single technological development escalate into such a prolonged, dangerous global standoff? Both sides built thousands of weapons, developed hydrogen bombs, created vast delivery systems, bombers, missiles, submarines.
And other countries followed. Yes. The UK, France, China, then later India, Pakistan, North Korea. Israel is widely believed to have them. Concerns persist about Iran's program. Proliferation became a constant worry.
And efforts were made to control it.
Yes. Most significantly, the Nuclear Non-Proliferation Treaty, the NPT, from 1970. It's become almost universal, with 189 members.
What's the basic deal of the NPT?
It's a kind of grand bargain. Non-nuclear states promise not to acquire nukes. In return, they get access to peaceful nuclear technology, like for power reactors. And the existing nuclear weapon states, the P5, the permanent members of the UN Security Council, commit to pursuing nuclear disarmament in good faith.
But it has challenges.
Big challenges. 4 nuclear-armed states, India, Pakistan, Israel, North Korea, remain outside the treaty. And progress on disarmament by the P5 has been, well, slow and inconsistent, leading to frustration among non-nuclear states. Enforcement is also difficult.
And beyond nations, there's the threat of terrorists getting hold of this technology. That's perhaps the nightmare scenario today. Non-state actors acquiring either a full weapon or enough fissile material to make a crude device. What's truly frightening here is realizing that even one such detonation in a major city would completely overwhelm any disaster response capability we have, let alone multiple attacks. The knowledge itself, how to build these things, can't be put back in the box. Vigilance is paramount.
And if nuclear war ever did happen between nations, the consequences are almost unthinkable, aren't they? Beyond the immediate destruction.
Oh, absolutely. We're talking about arsenals with thousands of weapons, many far more powerful than Hiroshima's. Even a limited regional nuclear exchange could throw enough soot and smoke into the atmosphere to cause a nuclear winter.
Blocking sunlight, causing global cooling.
Exactly, leading to widespread crop failures, global famine. Medical systems would collapse. Refugee crises on a scale we've never imagined. The environmental damage would be catastrophic and long-lasting.
It brings us back to the scientists who created it. The ethical questions must have weighed heavily.
Immensely. You see it in Oppenheimer's famous reaction to the Trinity test, quoting the Bhagavad Gita. "Now I am become death, the destroyer of worlds." Many Manhattan Project scientists wrestled with the morality of their creation. It perfectly highlights the dual-use dilemma of powerful technologies. Nuclear physics gives us carbon-free energy, medical isotopes for diagnosing and treating cancer, but also the potential for unparalleled destruction.
Knowledge itself isn't good or bad, but its application.
Precisely. If we connect this to the bigger picture, it's a stark lesson. Scientific advancement brings not just power, but profound ethical responsibility. How do we manage knowledge that has such potential for both good and ill?
Are there ongoing efforts towards disarmament today?
There are. Overall warhead numbers have come down significantly since the Cold War peak, thanks to treaties between the U.S. and Russia. But crucially, all nuclear-armed states are currently modernizing their remaining arsenals, developing new delivery systems.
So fewer bombs, but perhaps more capable ones.
That seems to be the trend. There's also the Treaty on the Prohibition of Nuclear Weapons, adopted by the UN in 2017. It aims for a total ban. However, none of the nuclear weapon states or their allies have signed it, so its practical impact is limited currently. There are also regional efforts, like creating nuclear weapon-free zones. Mongolia, for example, has declared itself such a zone.
It was such a complex, ongoing story. Bringing this discussion toward a close, the atomic bomb really does stand out, doesn't it? Arguably the most consequential invention of the 20th century. It changed warfare, geopolitics, our understanding of science's power.
And its potential dangers. It's that dual edge.
So what does this all mean for you listening today? Why is understanding this science, this history, still so vital?
Because the reality it created hasn't gone away. The fundamental knowledge of how to build nuclear weapons cannot be uninvented. It exists. This permanence places a unique and enduring responsibility on all of us scientists, policymakers, citizens. We have to ensure nuclear technology is used beneficially for energy, for medicine, while working relentlessly to prevent its catastrophic misuse. It leaves us with a critical question, I think. In an age where this knowledge is permanent, how do we, as a global society, maintain the necessary vigilance, the commitment to dialogue, and the pursuit of peace to navigate these risks safely?
That's a powerful and necessary question for us all to consider. Thank you for joining us here at the Urban Herald for this deep exploration. We hope this has been informative. We encourage you, as always, to keep seeking knowledge, keep asking questions. The more we understand our world, the better equipped we are to shape its future.